So welcome to lecture 4 of Advanced Thermodynamics and Fluid Mechanics. We're going to discuss today nonlinear and linear aerofoil theory. So what we're going to be doing is we're going to be combining our knowledge of shocks and expansion fans to try and assess the characteristics, the lift and drag characteristics of a supersonic aerofoil, and we're going to then try to see the look at a linearized analysis that's probably quicker at trying to estimate those lift and drag coefficients. So let's just start. There is a very nice YouTube video to understand transonic flows, and so I'll put a link in the blurb at the top, and so you can have a look at that, but that's something useful to look at. So let's just have a little discussion about what would happen if we take a typical aerofoil for that's appropriate at subsonic flows. This typically that's characterized by this nice rounded front and this very sharp edge at the back. and try to discuss the implications of trying to drive this at a faster flow, at a flow where compressibility effects are important, and a flow where the flow becomes sonic at some position. So as we look at the flow past any body, just purely the kinematic consequence of having the flow go around means that the velocity must go up. Let's say q is the speed, local speed, it must go up. And so if we have a local Mach number, then there is the possibility that the local Mach number can become greater than 1, even though the Mach number upstream, let's call that m infinity, u infinity over c naught, c naught being the speed of sound upstream, u infinity being the speed upstream, there's a possibility that the flow can become sonic at some position. Just as an example that we've discussed in the past for flow past cylinders and spheres, if you remember, we're looking at the flow past a sphere. We know from your first year lectures or second year lectures on flow past cylinders that the irrotational theory says that the velocity at the sides for a cylinder must be at least twice, or is twice, the upstream value. And this means that the local speed of local Mach number is going to be 2u infinity over c. Now, what we can say is that if we take an upstream Mach number of, let's say, 0.5, then the Mach number in the vicinity of the sides has a tendency to be about close to 1. And so although the upstream value is less than 1, we have the potential of creating sonic flow conditions, possibility of shocks and expansion fans at the side as a consequence of the flow going through this sonic state for cylinders. And we saw that in the discussion of the experimental observations of the consequence of raising the Mach number from 0.5 up to 1.2, the production of these shocks at the side. Now for a sphere, the increase, because we've now got three-dimensional effects, the increase in speed at the side of a cylinder is not twice u infinity, it's just 1.5 times u infinity. So the upstream Mach number, whether the upstream Mach number has a value of 2/3, then you can start to have sonic flow state at the sides, because it's going to be 2/3 times 3 over 2, which is 1. Now, what we have in all these particular cases is what we call a critical Mach number, m crit. And that is a Mach number where an upstream Mach number at which the flow becomes sonic at some point. Now, as you probably expect, the the greater the blocking potential of the obstruction, in this case it was a cylinder, the lower the value of U crit. And so we have this idea that something that is thin and streamlined has an M crit which is quite close to 1, and something which is large and blocking has an M crit which is much lower, maybe about 0.5, usually it's about 0.87. So these three figures here kind of show the consequence of increasing that upstream Mach number. When it's below the critical value, there's nothing really going on. Flow looks more or less like it's an incompressible flow down an aerofoil. When M infinity is equal to M crit, there's going to be a point where the flow is likely to be sonic. If we're above that, then we start to end up with some rather interesting localized behavior. So although the upstream value of the Mach number is bigger than U crit, it's less than 1, and which means far away from the aerofoil, the flow is subsonic. So far away it's subsonic, and in the vicinity we've got this kind of sonic flow condition. It's going to be supersonic. So the perturbation that's generated by that flow disturbance is going to tend to be quite localized, with obviously a certain weight coming at the end. Let's have a see what happens when the Mach number increases further. So what we end up doing as the Mach number increases further, still with M infinity less than 1, then we end up with a production of a normal shock at the back, underneath, and with time what will happen is they'll kind of move to the end, and this entire region will fill up to the supersonic flow region starts to touch or make contact with the upstream nose of the aerofoil. The normal shocks move the edge, and as the upstream Mach number increases beyond 1, what we end up with is a very rapid switch to an altogether different state where we've got a bow shock upstream. Now bow shocks upstream mean that we have essentially a normal shock upstream of the lifting surface. We have a subsonic region upstream of this, so we have a transition from supersonic to subsonic. We have a sonic line across which the flow becomes supersonic. Downstream, we have the flow is turning and must be deflected. Must be deflected back to horizontal flow condition, and so that necessitates the production of a shock wave. Now what you'll see here is that this bow shock gives rise to a very large pressure differential, and this increases the drag on this aerofoil by a significant amount. And so actually this isn't a very useful lifting surface for supersonic flows. This rounded front leads to the production of these bow shocks, and bow shocks are quite disastrous in terms of their drag properties. But they are useful when we come to look at or discuss re-entry craft, atmospheric re-entry craft. Then we'll see that the use of bow shocks are quite important, because they not only increase drag, but they also reduce the heat transfer to the re-entry craft, which means that the transfer of heat to the craft itself is greatly reduced. So this kind of contrasts those lifting surfaces of subsonic and supersonic, as we've said before. The characteristic of a subsonic airfoil is this nice smooth front, which means that drag is reduced, and a pinned sharp edge at the back means that lift is fixed and large. And so any lifting surface has to have these two things. Without the sharp trailing edge, then your lift will fluctuate, and that means it's not very useful. Without a smooth front, the drag becomes disastrously large, and it's not a lifting surface. So in order to control the control better the flow state past a supersonic airfoil, you really want to pin those flow structures down at the pin them to the aerofoil, and this is done simply by making those the surfaces flat with very, very sharp edges. And this does the main thing it does is it limits the production of a bow shock, so bow shock disappears. Now this isn't, the challenge obviously in terms of design is that the supersonic airfoil is absolutely disastrous at subsonic flows, and so the way that you typically design a lifting surface to operate at subsonic and supersonic flows is either you have its form changing geometrically with the backward swept wings, or you have a morphed wing which has very good lift characteristics at subsonic flows and very low drag characteristic at supersonic flows. So there is quite a bit of modification there. And so for a supersonic airfoil, the characteristics are that both the leading and trailing edges are sharp and they pin the flow down. Now, just to get the kind of sense of the direction, is that typically we describe the drag as being in the stream direction and the lift being in the cross stream direction. Now let's just have a little look at the characteristics of this. Now, the usual thing of a subsonic aerofoil, or people say, is that the top of the airfoil is a region of low pressure because the flow is going faster, and the bottom is a region of slightly higher flow because it's going slower. But this is actually not necessarily correct. It is the presence of the sharp trailing edge means that the circulation around the aerofoil is fixed. The sharp edge means for steady flow conditions that the flow must come smoothly off, and this pins the circulation, which is negative, around the aerofoil. But that's kind of a notional view that it's the pressure differential which gives rise to the direction of the lift force, in this case being vertically up. For a supersonic airfoil, we have this system of production of shocks and expansion fans, and if we were to follow a streamline coming in, we would see that when it meets the aerofoil, it must be deflected. And as we met in our lecture 2, that deflection must lead to the production of an oblique shock. Now, an oblique shock means that there's obviously a pressure rise. So P goes up. One of our main results in our discussion of the characteristics of normal shocks and oblique shocks means the pressure rises for shocks. If we follow a streamline coming along the top, then we see that it must be deflected down because it's turning a corner. Things that turn corner generate expansion fans, and expansion fans are regions where pressure goes down. Now, if we follow those streamlines along, and we'll see this as a feature of all these things, is that they must follow the shape of the aerofoil, which means that in the top we must have 2 expansion fans, and then as the flow turns at the end, there must also now be a shock. Now, we're not so interested in after the trailing edge because they don't lead to a change in the pressure differential around the aerofoil in this particular case, and so it's not important that we consider that component. And so we have these 2 regions where the pressure is low at the top and high at the bottom, and this gives rise to a net force pushing the obstacle up and giving rise to a net drag force. If the drag force is obviously negative, then there's an error in your calculations. So we use that as a kind of sanity check. So let's have a see how we do that calculation. So the kind of standard case is to take a flat plate. A flat plate is not such a bad example. It is literally a case of an aerofoil that's very, very thin. But it's a good starting point. And so if we've taken out our aerofoil as being 3 degrees and we take the upstream to be a static pressure of 100 kPa and a Mach number of 2.3 and temperature of 273 Kelvin, then we can do a couple of things. We can calculate the velocity upstream. So if we are given this information, then we can calculate the velocity upstream, which is obviously the Mach number upstream, so that's U1, times square root gamma RT1. So we know U1, that's a good thing to know. Now, as the flow comes along, we've got the fact that at the top it's going to have a turning angle of 3 degrees, and as the flow is going along the bottom, we know it's going to have a deflection angle of 3 degrees. And so in both those cases, we can appeal to either our expansion fan charts for Pantelmeier expansion or our shock charts in order to find out what the pressure is in regions 2 and regions 3. And so this is what we find. So with the shock charts, we find a pressure differential, and we find out the pressure in region 3 is 120 kPa. I think I've used a shock chart here, not a calculator. As I said, the Virginia Tech have a very nice compressible flow calculator. You can also get something similar on Google Play. So we've used that in the past. I think the web-based one is really clear, nice interface, written in Java, all that kind of stuff. So that gets the pressure in the lower region. That was get the pressure in the top region. So the pressure in the top region, what we're given is we're given an initial Mach number, the deflection angle using our critical reference state allows us to determine the Mach number in region 2, which is 2.4. Now remember about expansion fans, the thing that is conserved, the stagnation pressure. So P0 is conserved, it's an isentropic process. So knowing the Mach number in region 2 allows us to find out P2 over P2 Knowing the Mach number in region 1 allows us to find P1 over P1 P1 is a stagnation temperature, stagnation pressure in region 1. Now, since they're both the same, since they're conserved quantities, then we can kind of do our kind of cross cancelling in order to work out what P2 is, in which case it's 6 kPa. So we know two things. We know the pressure in region 2 and pressure in region 1. Now, pressure pushes. So if we have a kind of a region, P always pushes out. Yeah. So an extra wall, P is pushing perpendicular surface. So if we want to assess the forces on our aerofoil, then what we need to do is to find out what the force is on an element. Now, we're lucky in this case because this is a flat plate, which means that the force on that flat plate is simply the difference between the pressure in region 2 and 3 times by its length. The properties are uniform in this region. And so the normal force is P3, so normal force is in the y direction, and so P3 is pushing up, P2 is pushing down, which means that it's P3 minus P2 times length. And remember the units here. Pressure is newtons per meter squared, so this is a pressure times length, which gives us Newton per meter. So putting this together, we get 34 kilonewtons per meter. Given a length, I think we probably define this length to be 1 meter. Now, as engineers, we work in a kind of a dimensionless form, and so the key characteristic that we're interested in is the lift coefficient and the drag coefficient. Now, for streamlined bodies, which tend to be quite thin, the lift and drag coefficient are defined by taking the force and dividing by nominal pressure, half rho u squared, times the length. If we take a bluff body, like a cylinder, then the length scale that we're interested in is a cross stream distance. For a lifting surface, it is the length. And so in this particular case, we define a drag coefficient, CD, as 5, drag force over half ρ1 u1 squared times L. These are values that are upstream, a nominal estimate of pressure, or dynamic pressure, times the length of the aerofoil. Same for the lift coefficient. Those lift and drag components are determined by resolving the normal force in the streamwise and cross-stream direction. So as we see here, Fn is perpendicular, Fl is vertical, so Fl is Fn times cos alpha and Fd equals Fn sine alpha. Formula here. All pretty straightforward. Now if we put in those values using our nonlinear analysis, is that we get a drag coefficient of 0.046 and a lift coefficient of 0. What's the first thing you can notice is that, well, lift is more significant than drag, and that's what we expect for a lifting surface, that we expect CL over CD to be quite large. The second thing we kind of notice is this is quite hard to calculate because we're going through a series of steps, and it doesn't really tell us the relationship between lift and the angle, or lift and the any other geometrical properties available. And so we need another way of looking at this, which is a linear method, which is reasonably accurate for small angles. Yeah, so one thing we need is U1 and ρ1 in order to do our non-dimensionalizations that we work out from the upstream state. So we're going to look at a linear method of estimating the lift and drag properties. And this is actually going to be based on the assumption that the deflection angle is going to be small and the changes across the shock or expansion fan are negligible. So how we develop this linear analysis is we try to find a differential relationship between the change in pressure and how the flow is deflected. So we're going to assume in this particular case the flow is coming along and the flow is deflected downwards. So this would be like an expansion fan. What we're going to see, in actual fact, when we finish the analysis, is that both very, very weak shocks and expansion fans can be dealt with within the same framework, and merely by letting the angle of deflection be negative or positive. So in this particular case, the angle is down, which means there's an expansion and the pressure decreases. Now the shock angle in this case, or wave angle, is alpha m, which is arc sine 1 over m. We're going to try and find how the pressure changes across here. So conservation of momentum power interface, we've done this before for the expansion fan, which tells us that the U1T equals U2T, which combines together. The tangential component is essentially the normal, the velocity times cosine of the angle alpha m. So this is why U1T is equal to the left hand side U1 cos alpha m, and UT, remember we've got alpha m here and we're adding on a dm, which gives us the right hand side. We use a double angle formula, cos equals cos minus sine. Remember, for the small angle approximation, cos of d nu equals 1, sine of d nu equals d nu. And so this approximation allows us to rearrange U1 and U2 to show that the difference U2 minus U1 can be related to the deflection angle. That's kind of result number 1. Now we're going to look at how the pressure differential changes. Now to look at pressure differentials, obviously the best thing to do is use the conservation of momentum normal to this expansion fan interface. And what we know from the conservation of momentum normal to that is that the increase in momentum flux equals decrease in pressure. Of course, the momentum flux can be expressed in terms of the momentum flux normal to, because it is the flux normal to this interface, and so this ends up being rho 1 u1 times the difference in the normal velocity. The other way to see this, as we've had before, is rho 1 rho 2 u2 n squared minus rho 1 u1 n squared equals minus p2 minus p1. And to go from here to this form, all we're doing is we're noting mass conservation says rho 1 u1 n equals rho 2 u2 n, and that allows us to find out the change in the normal velocity and relate it to the pressure differential. What we're really seeking is, we already know d nu is proportional to du is proportional to d nu. Now we're trying to find du is proportional to dp, and then we're going to combine them together to show dp is proportional to d nu and find out what that coefficient in there is. That's what the main steps are. So the pressure differential P2 minus P1, we can normalise by half rho 1 u1 squared. Algebra, nothing really complicated. It's using sines and cosines, and ultimately we end up with trying to well, we've got here u2 minus u1, so we've got an expression for that difference from the previous page. A little bit of algebra, nothing really complicated, and essentially tells us that the change in pressure across that interface divided by rho 1 u1 squared, so that's dimensionless, is equal to minus 2 d nu over square root m squared minus 1. So that tells us the change in pressure is proportional to the deflection angle. So in our sense, the deflection angle at the moment is negative. It means the pressure goes down. Let's suppose the streamline goes up. So d nu is now negative. It tells us the pressure is increasing. And the trick about this linear description, it applies both to shocks and expansions, just merely by changing the sign of the expression. As we met in lecture 1, we had discussed the isentropic, what happened in the case when the strength of the shock decreased and the pressure differential became pressure ratio became 1. In this case, the flow tended to be the isentropic approximation would seem to be a good description of what that pressure differential looked like, and so that's what we're really exploiting here. So if we go back to our previous aerofoil and ask ourselves, estimate now using this linear description what the force is, and then let's see what this gives. So remember the formula that we've got P2 minus P1 over half rho 1 u1 squared is given by the deflection angle d nu divided by square root of m1 squared minus 1. Now the deflection angle is so small, actually the Mach number doesn't change as you go from left to right, so we won't take that into account. But what we will do, just to simplify some of this, sometimes I think the best way to do it is to put everything as a constant, where a is half rho 1 u1 squared over square root m1 squared minus 1, and that kind of makes the algebra a bit easier. Now taking this formula above here and applying it, let's see what it gives us. Well, the first thing is that the top tells us that P2 minus P1, the deflection is going to be down, so that's expansion, that's in the sense that we had before. And so P2 minus P1 is equal to minus 2 alpha over square root of m1 squared minus 1. So the deflection in this case is alpha. That's the streamline deflection, and that allows us to calculate P2. Now in region 3, what we have now, the problem's kind of flipped over, it's rather than the streamline going rather than the flow being expanded, it's turned a corner, it's been compressed because it would essentially strike the aerofoil. the deflection in this particular case is actually minus nu. So what happens when you put the formula in is that you find out the pressure increases, and that increase is equal to proportional to 2 alpha squared and 1 squared minus 1. So P3 increases, P2 decreases, and so that pressure differential will give us an indication of what the force is. Now I kind of get confused sometimes with all of this, and so the best way to do it I always find is basically draw a figure, work out where your expansion fan is and your shock is, and then find the deflection angles of the local streamlines, and then determine what the sign is going to be. The easiest way to work it out. So we can look at the pressure differential because we've got, as we had before, P2 is equal to P1 minus A times 2 times alpha. P3 equals P1 plus 4A alpha. We can find the pressure differential of P3 minus P2. Sorry. And so P3 minus P2 is equal to 4A alpha, and that allows us to calculate what those coefficients are. So let me go over here. So normal force is P3 minus P2 times the length, which is 4 alpha L times a half rho 1 U1 squared divided by square root of M1 squared minus 1. So dimensionally that makes sense. We put those values in, we can now resolve that normal force in the, sorry, my drawing's really bad, in the streamwise and the cross stream direction, and we can determine the lift and drag coefficients. So noting that alpha in this case is in radians, so it's not 3 degrees, so alpha is actually 3 pi over 180 rad. Then we can determine what the lift and drag coefficient is with this linear approximation. And so we put those values in, we get a value of 0.0459, which is different from the nonlinear case, but not far. 3 degrees. If the angle of inclination was smaller, then it would be more accurate. The lift coefficient is far larger than CD, and here it's about 0.1, and the nonlinear description gives me 0.092. So reasonably close. Just bear in mind you need to work in radians. You can do some open flame calculations, so this is a kind of terribly poorly resolved stuff, and the point I just want to get across to you is that it's really poorly resolved, but it's a reasonable estimate compared to CFD. I can do better with this, but I just kind of do a simple run. So the values are pretty okay. So we had our regions 2 and 3. Region 3, region 2. Estimates are reasonably good. Now we can apply this to more complicated geometry, and you'll see in the tutorial sheets an array of two-dimensional aerofoils, similar kind of thing. Now when you're trying to answer these types of questions, the trick is, I always say, is just draw a really big figure. Use as many coloured pens as you like, just draw a big figure, not a small figure. Calculate your deflection angle. So one of the things people kind of forget is that stuff they learned a long time ago, the sum of the opposites equals pi minus something else. There are lots of geometrical formula for working out angles, and so you need to do that a bit carefully. The area where I would make most mistakes would usually be on the angles if I rush it. So what you do is you have a look at your problem in this particular case, and what you notice in this particular case, the way I've drawn it. Remember, if you choose beta to be smaller than alpha, then you'll end up with your shocks and your expansions in slightly different places. This doesn't matter because ultimately it will give you the same result, but so you have to just be consistent in the way you draw it. So if it does say, you know, if you've got an angle here of beta and this is twice beta, then of course this is obviously 2/3 along from one end, and even I've not drawn it as well as I could have. It's pretty okay. I should probably draw it over there, but these are small angles, and so we are really thinking the limit that is a flat plate, and alpha and beta and gamma, or alpha and beta are small. So in this particular case, the incoming streamline comes up. It's squashed. Well, it'll hit the aerofoil, so it's deflected up, which means it's a shock here. It must turn that corner. Yeah. So that this angle 3 beta is the sum of 2 beta and beta. Now, as it turns the corner, it must produce an expansion fan. And then as it meets the tail end of the aerofoil, it must be turned again, so there must be a shock. Now, we're not interested, or you can be explicitly asked to say what the pressure is in the regions and also downstream, but we're not looking at those differences. We're just looking at the processes around the aerofoil. So while we might draw a shock, we won't calculate the region downstream. Along the bottom, the base of the aerofoil, flow comes along. It will otherwise hit the aerofoil, so it must be deflected down, and that deflection gives rise to also a shock. So if we were looking at this problem, what I would say, if I was to write it out really quickly, I'd say P2 minus P1, the flow is going to be, the pressure is going to go up, and so I'm going to have 2 times A times the angular deflection. And let's have a look at those angles. So we've got an aerofoil that's an angle alpha above the horizontal, and it's got a base of, it's got one end is beta and the other end is 2 beta. So we need to calculate what those the angular deflection is upwards. So if we look at the line parallel to the base, yeah, that has an angle of alpha. Since the total angle is 2 beta, the deflection up must be 2 beta minus alpha. Work out that quite carefully. So P2 minus P1 is going to be positive 2 times A times the deflection angle, 2 beta minus A alpha. So we look at region 3. As I say, it's deflected, and that deflection angle is the sum of the opposite two angles, 2 beta plus beta, which is 3 beta. So P3 minus P2 is 2A, deflection angle beta, and there's a minus sign here because the pressure is obviously going down. And I've got region 4, pressure's going up. Just going to write at the top, P4 minus P1 is 2A alpha, and P4 is going up, so that's all. So I'm happy with all of those. The question that you might have is that now we've got a P2 in here, so we have to get rid of that P2 and replace it with a P1. So what we do is we add these together. So P3 minus P1, we're adding these together. I always get the kind of mass kind of stuff wrong, so that's going to be 4 beta minus 6 beta minus 2 beta, and there's a minus, so I get minus 2A alpha plus beta. So now we have everything in terms of A's, P1s and A's. Obviously, you know, with a little bit of thought, we realise that maybe upstream static pressure doesn't really play much of a role in these linearized calculations, because obviously it's pressure differences. And so one way to kind of simplify this is to then ignore in our next bit of calculation the P1s. If you wanted to check whether the algebra were working, then you explicitly put it in, but otherwise I know it's not going to be a feature in the final result, and so I don't put it in. That's how you'd kind of do the calculation. Let's see what we produce. So we've got our, as we've got here, our P2 minus P1, P3 minus P2, P4 minus P1. So I've got all of that together. And, and this is missing an A. naughty. So we know our pressures in different regions. Now we have to calculate forces. So, and we've got a couple of things. We've got to not only calculate the force, we've got to resolve them in a certain direction. So since we're interested in the streamwise and cross-stream direction, we have to resolve those normal forces drawn in blue in the cross-stream. And so here we have to take into account the fact that, for instance, in order to resolve the force in region 2 in the streamwise direction, then what we're doing is we're doing F2 normal times sine of 2 beta minus alpha. It is in the direction downstream, so that's positive sign, and we're going to use small angle formula, so that's 2n times 2 beta minus alpha. And if we're doing in the cross-stream direction, that's the 2 times the normal force times cosine. That's minus because the force is pushing down, and we're resolving in the up direction, and so that's 2 minus f2n cos 2 beta minus alpha. And actually, because it's small angle, it's just minus 2 fn. And what we find is, because we're doing the small angle approximations, when we're looking at the normal force, actually we don't bother with these angles. These angles, since it's a cosine, they kind of cancel. Well, not cancel. They're equal to unity or close to unity. But we do need those important contributions when we're looking at the drag force. And what we find is the drag force is going to be a quadratic dependence on the angle, and the lift force will have a linear dependence on angles. So as we add those components together in regions 4, regions 2 and 3, when we're looking at the resolved components by taking the cosine of the angle of the normal to the vertical, then we find they're close to 1, and then we can just combine the results for f, p4, p3, 2, p3, and get our answer for alpha L. The lift coefficient obviously has to be the force normalized by half rho 1u1 squared times the length, and all together that gives us 4 alpha times the square root of m1 squared minus 1. Remember, this is a small angle approximation, and m1 is bigger than 1. Same for the lift, but the lift is a little bit more complicated. Sorry, same for the drag, but the drag is more complicated because the signs of these angles of the normal to the vertical are non-zero, even though the angle is small, and so we end up with using a small angle approximation, and in the end we end up with a kind of quadratic functions of angle. Putting that together in this particular configuration, we end up with the drag force is 4 alpha squared plus beta squared. Remember, alpha and beta are in radians, and divided by square root m squared minus 1, valid for high Mach number. And so what do we have here is if we look at the lift coefficient versus Mach number, we kind of have, typically when we make these measurements, we kind of have two regimes. We have a low Mach number where the result is kind of weakly dependent on Mach number to about 0.3, as we said before. 0.3 is a reasonable estimate in most cases for the flow to be a good approximation is an incompressible flow state, but that has a very weak dependence on Mach number. The drag has a subcritical Mach number where the flow becomes sonic at some stage, and drag is lift is increased. Drag is also increased. I haven't plotted drag on here, but I should get that out. And as the Mach number increases, then we see a very rapid decrease in the lift coefficient. Now let's have a see what we know from before. So we know from our work on aerofoils before that the CD is a constant for low Mach number, and we know that the lift coefficient has the 2 pi alpha. So the slope of the lift gradient is 2 pi, which we studied from the conformal mapping with a circulation that sets the stagnation point at the rear of the lifting surface. So as we remember, the circulation is set as to be a negative value so that the flow peels off smoothly at the end. and this is sufficient to set the gradient of the lift line to be lift coefficient to be 2 pi. At high Mach number, which we've covered now, we see this quadratic dependence on angle, and we see a linear dependence on angle for the lift coefficient. And we had our, remember, our m squared minus 1 take the square root. So for high Mach number, we obviously expect if this analysis could be extended by high Mach number, we would expect a kind of relationship like that. The reality is that other kind of things kind of crop in at higher Mach number, but that gives us a strong indication the lift coefficient will decrease with Mach number. So that concludes our discussion of forces on aerofoils from nonlinear and linear analysis. As you see, we've combined our understanding of oblique shocks with expansion fans to be able to estimate the change in pressure around the flow structure, and from this the lift and drag coefficients. Okay, thank you very much. See you soon.